Welcome to The Explainer. I am absolutely thrilled to have you here today. We're going to dive straight into a really fascinating journey, starting from the basic, invisible physics of magnetism all the way up to the incredibly complex, precise movements of modern robotics. If you've ever looked at a robotic arm, a drone, or an autonomous vehicle and wondered exactly how it translates raw power into such deliberate motion, well, you are in the perfect place. So let's get right into it. Now, think about this for a second. It really is a profound engineering problem. How in the world do we take something as unstructured as a simple stream of electrons flowing out of a battery and transform it into the delicate, lifelike stride of a humanoid robot, or the precise spin of an underwater drone's thrusters? It honestly seems like magic. But as we're going to see together today, it all comes down to some incredibly clever mechanical and electrical engineering. Here's our roadmap for today. We'll start with the magic of magnetism, then break down the anatomy of a DC motor. Next, we'll look at the commutator's clever trick, followed by how we control speed and direction. Finally, we'll wrap up with powering the robotics revolution. Understanding these foundations is going to completely unlock the secrets of real-world robotics for you. All right, Section 1, the magic of magnetism and the invisible forces at play. So there are basically two types of magnets we deal with in motor design. On one hand, you've got your permanent magnets. You're definitely familiar with these. Their magnetic field is fixed, it's always active, and their north and south poles never change. But then we have electromagnets, and this is where the real magic happens. By just passing a current of electrons through a simple copper wire, we generate an electromagnetic field. The absolute game changer here is control. We can turn an electromagnet on, turn it off, crank up its strength, or completely reverse its poles just by tweaking the electrical current. To really grasp why that happens, we gotta zoom way, way in. This brings us to magnetic domains. Think of these as microscopic neighborhoods inside ferromagnetic materials, like iron, where atoms align their magnetic properties. In normal, unmagnetized iron, these neighborhoods are pointing all over the place and totally cancel each other out. But hit them with some electricity through a wire wrapped around that iron, and bam! Those microscopic neighborhoods suddenly snap right into alignment in the exact same direction. As more current flows, more of these domains align until the metal reaches magnetic saturation. We've literally just transformed a basic piece of metal into a fully controllable magnet. Now, how do we actually turn that magnetic field into physical pushing and pulling? I invite you to physically hold up your left hand right now. Seriously, do this with me. This is Fleming's left-hand rule. Point your first finger straight ahead. That represents the permanent magnetic field going from north to south. Now point your second finger out to the right. That's the direction of the electrical current. Finally, look at your thumb pointing straight up. Your thumb shows the actual direction of motion. When you put a current-carrying wire inside a magnetic field, it experiences a physical mechanical force. That literal push is the absolute beating heart of every electric motor. Moving on to Section 2, Anatomy of a DC motor. Let's start building this machine. Let's isolate the core components of a brushed DC motor. Surrounding everything on the outside, we have the stator. In this case, permanent magnets creating a constant magnetic field across the center. Inside that field sits the rotor, or the armature. That's the part that actually spins. We apply voltage to the armature, which turns it into our electromagnet. And because of Fleming's rule we just talked about, the magnetic field of the stator pushes against the newly formed electromagnetic field of the armature, forcing the whole thing to rotate. Now check out the real-world complexity of a wound armature. A single loop of wire, well, that creates a pretty weak force. So instead, engineers wrap dozens, sometimes hundreds of coils of copper wire super tightly around the armature core. This dramatically amplifies the electromagnetic field. It gives us significantly more torque or rotational pushing power than a single wire ever could. But here is a truly surprising piece of engineering. The armature core isn't just a solid block of steel. The rotor is actually made up of multiple thinly sliced iron discs that are laminated and insulated from one another with a layer of lacquer. Why go through all that trouble? Because if it were a solid block of metal spinning inside a magnetic field, it would generate these swirling, wasteful internal electrical currents known as eddy currents. These currents create a ton of heat and just kill the motor's efficiency. By slicing the metal into thin discs, engineers effectively stop those eddy currents right in their tracks. Brilliant, isn't it? Section 3, the commutator's clever trick. Let's solve the infamous dead center problem. Imagine the armature is spinning along nicely. What happens when the electromagnet aligns perfectly with the permanent magnets? North hits south and, yep, it gets completely stuck. It hits an equilibrium position called dead center, and all that rotational force drops straight to zero. If we don't do something, the motor just stops dead. Enter the commutator. This is a rotator electrical switch attached directly to the shaft, made of segmented copper plates. Brushes rub against these plates to deliver the power. Right at that exact dead center moment, the gap between the commutator plates passes the brushes, which automatically reverses the direction of the current flowing into the coil. This instantly flips the magnetic poles of the armature. Suddenly, north is facing north again, pushing it away, and the motor keeps right on spinning.
And that right there is exactly why practical motors use multiple coils and multiple commutator segments. If you only had one single coil, the motor would be incredibly jerky and could easily stall out at that dead center point. By having multiple coils spaced out, it operates almost exactly like a baton pass in a relay race. As one coil approaches that dead zone, another coil is perfectly positioned in the magnetic fields to take over the rotational force. This produces overlapping torque curves, giving us smooth, continuous power and a steady speed, even when the motor's under a heavy load.
All right, Section 4, controlling speed and direction. Let's get into the electronics. The solution for controlling direction is just beautifully simple. It's called an H-bridge. Remember, to reverse a DC motor, we have to reverse the polarity of the voltage. But obviously, we can't manually unplug the battery and flip it around every time a robot needs to back up. So, the H-bridge solves this by using 4 semiconductor switches, usually MOSFETs, arranged in the shape of an H, with the motor sitting right in the middle crossbar. Let's actually trace the electrons here. If the controller turns on switches Q1 at the top left and Q4 at the bottom right, the electrons flow diagonally down, passing through the motor from left to right. Boom, the motor spins forward. To reverse, the controller simply turns off Q1 and Q4 and turns on Q2 at the bottom left and Q3 at the top right. Now the electrons flow diagonally the other way, passing through the motor from right to left. It's an incredibly simple but powerful logic gate that instantly reverses the motor's direction without a single moving part outside the motor itself.
So, we've got direction covered. What about speed? You might think we just lower the battery voltage, right? Well, actually, scratch that. Doing that is super inefficient. Instead, we use something called pulse width modulation, or PWM. We don't send a continuous, flat DC voltage. We rapidly pulse the full power on and off, literally thousands of times a second. The motor is mechanical. It can't react instantly to a millisecond power drop, so instead it just reacts to the average voltage of those rapid pulses. We measure this using the duty cycle, which is just the ratio of how long the pulse is on compared to the total time. If the duty cycle is narrow, let's say it's only on 10% of the time, the motor sees a very low average voltage and spins slowly. But by simply widening that pulse, bumping the duty cycle up to maybe 80% or 90%, the motor receives a much higher average voltage and spins way faster. This gives us incredibly precise, completely digital speed regulation. And finally, Section 5, powering the robotics revolution. Let's put all this into practice. Because of the crazy precise control we get from H-bridges and PWM, DC motors are the undisputed muscle of modern robotics. Just look at the diversity of applications. They're steering autonomous mobile robots and vacuuming your living room floor. They're providing the exact torque needed for massive manufacturing robotic arms to weld cars together. They're replicating human gaits in medical exoskeletons to help people walk again. They're even managing the precise depth and stability of autonomous underwater vehicles mapping out the ocean floor. This entire journey really boils down to this one core thought. DC motor controllers offer precise control over motor speed, position, and torque, which is essential for accurate and repeatable robotic movements. Think about it. A powerful motor is absolutely useless if it's clumsy. It's the brilliant synergy of the armature, the commutator, the H-bridge, and PWM pulsing that turns raw electrical power into the delicate, repeatable precision that completely defines a modern robot. We've gone from the invisible alignment of microscopic magnetic domains all the way up to the digital code dictating a robot's speed. You now understand the fundamental building blocks of electric motion. So, my final question for you is this. Now that you hold the keys to this incredible technology, what kind of robot are you going to build? Thank you so much for joining me on this explainer today. Stay curious and keep learning.